Hey folks, today we're talking about springs and elastic potential energy. Springs are something that exert what is called a variable force. Now, the truth of the matter is that all forces that we've ever talked about are mostly variable forces. In rare situations when like nothing's moving or things have been established for a long time, we can say that the force is constant, but mostly forces are variable. Like if you push on something, you don't automatically push on it with the maximum force possible. You go from zero very quickly up to some force, and so that's a variable force. So we study springs because the variable force is very dependable. And so we have a law that describes the force that a spring exerts, and then there's a certain amount of energy associated with it. And so for springs, what we mean is every spring is built at a certain length. If you change the length of the spring will start to exert a force on the things that are stretching it. Or compressing, but the spring doesn't compress. What you would notice if you had a spring in your hand is the more you pulled on the spring, the harder the spring pulls back on you. So that's our one variable force that we focus on for this course. That variable force for springs is described by what is called Hooke's law. So if you want a law named after yourself, then study something that no one studied and come up with some relationship. So Hooke's law is written like this. The absolute value of the spring force is equal to K times the absolute value of X. And so there's kind of a lot to that. So the intuitive nature of this is if I pull to the right on this spring, it will pull against me to the left. So we'll talk about the absolute value signs. The three variables in here are the spring force, excuse me, and that's in newtons. K is known as the force constant. And I'll explain that in just a minute. That's going to be in newtons per meter. And then the value of X is the spring stretch. It is the amount that the spring has been stretched from its like resting position. So I want you to think, so this is in meters, and I want you to think of this as the amount of change in length from the rest length of the spring. So what I mean by that is this is the spring's rest length, however many meters that is. And as I pull it, I am increasing the length of that spring. So if I measure this length and then I measure this length, the difference between those two measurements are going to be the stretch of the spring. And so this is the relationship. The further you pull a spring, the more force it will exert on you. And it's directly proportional to the stretch as opposed to the length of the spring itself. The reason they're absolute value symbols is because the spring force and the stretch are vectors, and they are not in the same direction. The truth of the matter is the force that a spring exerts on the stretcher is the opposite direction as the actual stretch. So a spring force is exerted in the opposite direction of its stretch. So force and stretch are in opposite direction or directions. Okay. Now we are going to mostly leave Hooke's law alone because we have a whole unit on simple harmonic motion, so we'll study springs again. But one more thing, this force constant. It's newtons per meter, and it's basically the rate at which the force increases. So this is like a linear relationship that the spring force varies directly, linearly with the amount of stretch, and that ratio is the force constant. And so if something has like a large force constant, it's very hard to stretch it. If it has a low force constant like this one, it's very easy to stretch. So to kind of move on from this, we're going to imagine that we perform an experiment with the spring itself, and we say, sorry, just rearranging things. we would say, like, we're going to do this experiment and we are going to measure the amount of force that the spring exerts as a function of its stretch. And so we would have on the y-axis, we'd have the spring force. On the x-axis, we would have the stretch. The like y-intercept there would not be at like a length of 0, it would be at the rest length. So it would be when the spring is at its equilibrium or rest length, that would be where our graph starts. And so this graph would show a linear trend. And so to kind of like bring it back to force constant, this equation, the spring force equals k times x, is in y equals mx plus b format. And so the slope of this line is equal to the force constant. You are almost guaranteed a question about this on the AP exam, because this is one of the critical things to know about springs, is that if you graph the force versus stretch, you get a straight line where the slope is the force constant. So something like, with a very large force constant would have a very large slope, very steep line. Something with a small force constant would have a very shallow line. The thing that we are here to do is to focus on energy. And if you find the area under the graph, that is equal to the energy stored by the spring. So that's what we're going to do. So we take this graph and we find the area under some arbitrary amount. So we stretch it a certain amount. We do that as steadily as we can to get this line, and we find the area under the graph. Now the area under the graph is equal to 1/2 base times height, because no matter how you cut it, this graph is going to give you a triangle. And so the area under the graph is going to be 1/2 times x times the spring force, which is not that revolutionary. So it looks different from Hooke's law. The force is kx. This is force times x, so that's different. But the thing I wanted to show you is we also know that the force is equal to k times x. So if I do just a little substitution, I get the area is equal to 1/2 x times kx. Now the absolute value symbol is not very significant here. It's just saying you're always going to use positive numbers, so you're always going to have like the magnitude of the spring force, and it's up to you to decide which way it points. This is a little significant, and so we can combine these two terms and say the area is 1/2 kx squared. And so this is going to be important for us for energy. So our final idea today is the idea of elastic potential energy. And so it's a type of potential energy, which means it's energy that is stored. It's stored by a force. So you can think like gravitational potential energy was stored by the force of gravity. This is stored by the force required to deform an elastic object. So anything that stretches, in theory, obeys Hooke's law and has an energy that it can store that is equal to 1/2 kx squared. And so again, that's also a subject that is prone to AP physics questions of like, hey, here's a stretchy object, does it obey Hooke's law? And so the equation for elastic potential energy, it's U because it's potential energy. It's S because it is specifically about springs. So you can call it spring potential energy. I don't care. And it's equal to 1/2 kx squared. So this is our third and final equation for type of energy. We're going to introduce ourselves to more later in the course, but for this energy unit, there are three: kinetic, gravitational potential, and elastic potential. The final word about this is to say that the spring potential energy is 0 when the spring is at its rest length. So not the absolute length of the spring, but the distance or the length difference between stretched and unstretched. To put a kind of coda to this, we can now update our equation for mechanical energy to say it is the sum of the kinetic energy, the gravitational potential energy, and the elastic potential energy. So this is more or less the central equation of this unit. We will introduce other topics after we talk about mechanical energy more that kind of mess with this process, but that's for later. So that's it.